My name is Daala, and I work with both Tim Terryberry and Jean-Marc Bellin, and this is a paper we put together called Predicting Chroma from Luma using frequency domain instrument prediction. And then I added to the slide, encodings based on lap transforms. So that's really the motivation behind this talk, was that we needed a technique that would work with lap transforms. And so, why do we care about instrument prediction in the Chroma plane? In a force field image, the Chroma pixels are 50% of the Luma pixels, so it ends up being a third of the data. We decimate them because they're less visually important. And so when we do instrument prediction in most typical image and video codecs, we do it through spatial signaling. We'll send a mode, and then in the spatial domain, we'll predict what that block looks like from the decoded neighboring blocks. This is done mostly because of local coherency, and has the limitation that we end up doing it just based on the current color plane. We also have the restriction that forces us to have the neighbors already decoded, so it doesn't work when we have a codec that uses lap transforms, and it doesn't exploit cross-channel correlation, which is something I'll come to later in the talk. So I'm sure you're all familiar with this. This is just how spatial domain prediction works. Using a 1 pixel border of your neighbors, and instead of modes, you can select the mode that best extends that edge so that it matches the predicted image, or the image you'd like to code. And so we do this, many video codecs do this in both the Luma plane and the Chroma planes. However, when you have lap transforms, things are a little different. So for those who are not familiar with lap transforms in video codecs, this is something that's used in audio codecs quite a bit. The idea is that you apply a pre-filter across block boundaries that is invertible, and it has the effect of decorrelating the blocks along the block boundary. You then apply your forward DCT, do quantization, and then the decoder, you undo the DCT and apply the post-filter, which is the exact invertible version of the pre-filter. And so it's not going to come out so well, but visually, this is what the pre-filter does. It makes the image look blocky. And the idea here is that by doing this pre-filter decorrelation, you're able to get an improved coding gain, and you remove the blocking artifacts that arrive through quantization, because you're applying the inverse post-filter, which has the effect of smoothing along those block boundaries. And so this is a technique that we're using in the Daala video codec. It's also used in other image codecs like JPEG, XR, and DC1, with the idea of removing blocking artifacts. This has the problem, of course, that we can't do image prediction because we have to apply the post-filter before, or we have to apply the next DCT before we can apply the post-filter. So I have a better picture of that here. This is a decode pipeline of a codec using lap transforms. And so the red block is the one that we're currently trying to predict. Let's break it from the blocks in bold. But because we haven't been able to apply the post-filter, we don't have the spatial image data. So we don't have the pixels that are along this border here in the spatial domain to do a spatial prediction of the block in red. And so what let's talk to you today about is two techniques we developed for doing Chroma from Luma in a codec that's using lap transforms. So the first key observation to note comes from this paper by Lee and Cho that describes the relationship between the Chroma planes and the Luma planes. So doing a YUV color conversion has the effect of decorrelating the Luma plane from the Chroma plane globally, but locally there may still be a correlation. So you may have an edge, and in the Luma plane that edge is sharpened, and in the Chroma plane that edge is sharpened. But the correlation may not be a positive correlation, maybe a negative correlation. And so locally you could learn that correlation and exploit that, and that's what this paper talks about. So how does he do that? Both the encoder and the decoder compute a linear regression. Again, this is in the spatial domain, and so it's done across the border pixels in the spatial domain for each pair of Luma Chroma coefficients that are coincident. They're fed into this linear regression, and alpha and beta are estimated. then in the decoder, the reconstructed Luma coefficients from the Luma plane can be used to predict, or to create a predictor for the Chroma plane. So based on the linear regression, we're able to then come up with a Chroma predictor that's coincident to that Luma decoded plane. This, however, was proposed to HVC and not selected because to do this saw a 20-30% increase in complexity, of runtime complexity, in forming the predictor, because you have to do this linear regression on every block. And so that ends up being very expensive for both the encoder, or just for the decoder as well as the encoder. So what we did was in Daala, we adapted this technique to work in the frequency domain. And here the sort of key insight is that the lap transform and the DC are both linear themselves. So we have a linear regression or a linear relationship in the spatial domain. We apply two linear transforms. We have the same linear relationship in this new lap frequency domain. And so we do something similar. Here we do a linear regression on just the 4 lower frequency coefficients, and we do this because they cover the same spatial extent, but there's fewer of them. And so we pick those because they're we have the most influence in the horizontal, vertical, and diagonal directions. We again use the coincident reconstructed Luma coefficients to predict the Chroma coefficients. And here, I point out that we have two sets of model parameters, one for the DC, which has a constant offset, and one for the AC that has no constant offset because it's zero mean. And then if you compare this to doing it in the spatial domain, it's still expensive, but the cost is fixed with, or it's constant with the block size. And the reason for this is that regardless of the block size, we're only ever doing the linear regression with the 4 lower frequency coefficients. And so this is a technique that we had put into Daala, and we're using it to do prediction from Chroma from Luma in the presence of lap transforms. And so I'd like to show you kind of what this looks like. So here's the original uncompressed image of one of our test images. And so this has no quantization. And so let's go over this. And so as an example, consider doing this PVQ prediction for Chroma from Luma of the 15 AC coefficients of a 4x4 Chroma block. The 15-dimensional predictor R that we're going to use to predict that Chroma block is just a scalar multiple of the coincident reconstructed Luma coefficients. And we can see that directly from what we did with the frequency domain. This was our relationship, and that's just exactly some alpha AC times the reconstructed Luma coefficients. So this is exactly the same equation. And so if we look at what that does to the shape predictor, if we just replace that, you'll see that it's almost exactly the same as the reconstructed Luma coefficients, with the one exception that sometimes that correlation is negative. So as we said before, when you're computing that alpha AC, sometimes the relationship between the Luma plane and the Chroma plane has an inverse correlation. And so we would need to convey that relationship here, that sign of the AC of the linear coefficient. Right, so the only difference is the direction of the correlation. And so this is the entire Chroma from Luma PVQ algorithm. The first thing we do is we let R equal the reconstructed Luma coefficients. We compute theta. If theta is 0, the prediction is exact, so we put a skip flag, and that means we don't need to code anything further because the decoder will be able to see the skip flag and know that the predictor is exactly the reconstructed Luma coefficients. Otherwise, we compute and code a flip flag, which is just if theta is greater than 90. And that means on that projected 2D diagram, if the angle between the predictor and the input is more than 90, it's actually, the prediction is actually in the wrong direction, and that indicates a negative correlation. So if we were to compare the PVQ Chroma from Luma prediction with normal PVQ prediction that Tim just presented, these are the only two things that change. We would just code a single bit per block of Chroma, and that's our entire sort of signaling overhead there. And so in order to show this, we did a still image experiment. So here, this is just using 50 high-res images from Wikipedia that were downsampled to 1 megapixel, and then they were run through the Daala video codec with the 3 different Chroma from Luma prediction techniques. So no prediction, the frequency domain Chroma from Luma, and then this PBQ Chroma from Luma. And it may be a little hard to see, this is a log scale, but from most efficient to least efficient is the PBQ frequency domain and then the no prediction. And so there's actually a better way to compare these graphs is to compute the Pageant-Picard distance, which is just the average distance between those curves. And so in doing that, you can see that in going from no Chroma from Luma to just frequency domain on both the CV and CR claim, we picked up a few percent, and then going from no Chroma from Luma all the way to the PBQ Chroma from Luma, we picked up 6 and 4.5% on some of the metrics. So that's a pretty good gain for essentially no model fitting costs and nearly no signaling overhead. So we're very happy with that. And this is now the same master we ripped out the other one. So to conclude, this paper introduced these 2 algorithms for doing Chroma from Luma introduction and codecs that use lap transforms. One of them is suitable for use with codecs that do scalar quantization, and then one of them uses an extension of this gain shape quantization. And one of these sort of open questions is, people have noticed that given the presence of both the reconstructed Luma coefficients and the reconstructed Chroma coefficients from one plane, that can also signal the other plane. So the question is, can we do some kind of bi-prediction in PBQ using both Luma and CV? So that still remains to be seen. Like Tim said, we've got a bunch of resources online. The CfL stuff I talked about using frequency domain interpreter for the frequency domain Chroma from Luma, that's up on our demo pages, but we don't have a demo page that does this newer PBQ version of it. The next week will come soon. All right, any questions?